Welcome back, and now we are going to talk about those procedures related to the process of comparing two means. And so there's, of course, the confidence interval, which we're not going to spend a whole lot of time on. I'm just going to say hi to it, and then we're going to move on. And then we're going to talk about the test, because the test is actually what you typically use more in practice. Okay, so for a confidence interval, for a one sample case, when we had one population, right, we took x bar plus and minus the margin of error, E, right? And that margin of error was just that t critical value, t alpha over 2 as I call it, and then times the sample standard deviation over square root of n. Okay, same idea in a two sample case. Okay, the only difference is that we have two population means and we're looking at their difference. So that's why we do x1 bar minus x2 bar and then add and subtract the margin of error. And so here, the margin of error changes in the two sample case. Okay, so it's still that t critical value and then times your standard error. It's just that in the one sample case, we called the s over n our standard error. And now in the two sample case, and there's a comment down below about this, but the square root of s1 squared over n1 plus s2 squared over n2, that's our standard error here in the two sample case. Okay? So we can get a confidence interval, and then that's the mechanics of how to get the confidence interval. The interpretation isn't changing, which is why I'm not going to emphasize that. Okay? When we look at the test, the two-sample t-test, okay, the process, we're still going to set up hypotheses, and then we need to get a test statistic, and that's where this next piece comes into play. We have, at least in the one sample case, it was x bar minus our mu naught, and then over s over square root of n, again, our standard error. In the two sample case, very similar again, but we have two sample standard deviations, or two sample means rather, and so we take their difference and subtract the difference in the hypothesized means. So this typically, I'll tell you, typically in practice we assume this to be 0 because the null hypothesis assumes no difference. So typically this is 0, so you can simplify the numerator just a bit. And then the denominator, you're still dividing by your standard error, which in the two sample case is that square root stuff. Okay. The other thing to note is that when we're doing a t-test, right, it's going to ask us when we to calculate the p-value, we need to know degrees of freedom, df. Okay. So just so we're all on the same page, this is degrees of freedom. And in the one sample case, it was nice and easy to calculate n minus 1. Okay. In the two sample case, it's a little ugly if you want the exact number. And this is okay to get a decimal. Okay, that is perfectly okay. Some students think you need to round. Don't round. Okay. And then just so we're aware, I mean, so the calculation is long and tedious. Just be patient. Don't do many steps at once. Even myself, I have to do like when I calculate it, I do like this number, press enter, and then do this number, press enter, and then I write it down like so it's number plus number, and then I square it, and then like I go very much in step. If you want, you could maybe write a little Excel program to calculate this for you, a macro in essence, if you know enough about coding. The only thing that I want to mention is that sometimes if we're in a hurry, we might just want to estimate the degrees of freedom, and the conservative estimate, or the minimum value that you would get for the degrees of freedom, would be one less than the sample size in either case. So whichever, I guess, find the sample size in each case, subtract 1, and that would be the minimum value that it could be. It won't be that perhaps, but it's the minimum value. Then at most, it would just be the sum of the sample sizes minus 2. So the degrees of freedom can be between there. So that's at least a nice way to double check that when you do the calculation, is it between those two numbers, which are relatively easy to calculate? If it is, great. If it's not, oops, go back and redo. Okay. And then I mentioned about the standard error. Okay. So from here, once we get that test statistic, we need to get a p-value, right? And we already know the commands, right? Back in the one sample test case, we did, oops, I'm in the wrong, no, I'm in the right one. back in the one sample case, we said, okay, if you have, one side to the left, one side to the right, and two-sided, here are the p-values that you did, right? Same thing here, right? So we have a p-value. I'm in the wrong video. There we go. We have we have a test statistic, and we have the direction based on the null, or the alternate hypothesis, which is just going to have a little different form, but then we can get a p-value. Okay, so that's all we have there. With the hypotheses, I should just mention that when we set them up, we are looking for a difference. So by default, we say that the difference is 0, and then again, this is effectively that the two are equal. That's for most cases. If you have a specific different case, you could, say it's like mu1 is equal to mu2 plus 5. Okay, something like that. You could do that. And then your alternate would just be testing greater, less than, or not equal. Okay. Now, all of this we can do by hand. And then a half hour later, we might have, a part of the problem done, and then we still have to calculate degrees of freedom. And Excel is super nice because it's literally built into the data analysis tool pack. So if you, the only thing with this is you have to have the original data. Okay, so you have to be able to select the data and then put that into the tool pack. If you don't have the original data, you can't do this. So in most things that you are going to see from me, I'm going to give you the original data, and then we can just use the tool pack. However, there will be 1 or 2 exercises, at least in homework and maybe in class, where you have to do the calculations. I might have included a different adjective in front of there, but alas. When you go into the data analysis toolpack, so again, this is under data and then data analysis in Excel, there's going to be 3 t-test options, okay? We're not going to do the paired, okay? That would be if you had matched pairs. So that's not going to apply here. Then there's an equal versus unequal variances. Generally, we are not going to use equal variances, and in fact, never in this course at least. But even in practice, it's better to assume unequal variances, just because that's what life is going to be like. You can draw from 2 populations, and they're going to be similar, but they're never going to be identical, right? So that's why we want to use unequal variances. The equal variances case, we would tell you, and yeah. And also, actually, the unequal variances assume or has the equal variances built into it. So if you do unequal variances, it captures the case where you have equal variances. The other thing that you can do is just t.test in Excel in a command, and it'll lead you through it. I would avoid using that just because at least when we compare the p-values from the 2 methods, the second case doesn't give you the right p-value, which at least in sampling, you will need the correct p-value. So just be aware of that. Okay. And then the other thing just to mention is that when we're doing a one-sided test, and we'll see this in the next example, is that Excel automatically calculates your alternative hypothesis as a mu1 is greater than mu2, and then it actually assigns, despite the variable's naming, it puts the names mu1 based on whichever sample mean is larger. So even if you have them, like you have x, you have population 1, and then you have population 2, and then data, it could actually assign mu1 to population 2 if that sample mean is larger. Okay, so just be looking at the output and interpreting it correctly, and we'll see that in the next example. But otherwise, we have a lot to keep track of here. Doing it by hand, a little complicated, but we can get through it. And then by and large, the other parts of the structure that we've built so far with hypothesis testing remains the same. And then if we can have access to the original data, use Excel.